So we have essentially just one topic left to discuss, and that topic is, of course, neural nets. In principle, of course, there's a lot of things in the press and you hear about all the time, and it's, of course, the topic or the method that is currently the most used and the most successful. It's in principle very easy. Okay, we'll see the topics we'll discuss, what it is, how to train them. What to do is, on the one hand, very simple. There's no mystery to it. There's nothing particularly complicated about it. On the other hand, of course, to understand why these things work as well as they work, okay, of course, there's some theories, there's some explanations, but there's still a lot of it that's not known, and so you know as much as anyone else about it because nobody knows anything about that, okay? So we'll do the easy part, the part that everyone understands, and the rest, it's fine, okay? Good. So let's just go back, right? So the last maybe month or so, we have talked about unsupervised methods, right? Things like nearest neighbors and singular value decompositions and all these things. So we'll step back now again, and we'll talk again now about supervised. And so if you remember, how did this all work with supervised? Well, we have samples, we have X's and labels. Either we do classification or we'll do regression. Neural nets can be used for either of them. And then we have some particular family of functions. Typically, we started out with something like linear. And let's assume we talk about the regression task. We'll try to match these parameters so that they give us a good prediction, right? And so we have seen that in order to do well, one method that is, makes a big difference, and it can make all the difference in the world whether we're doing well or not, is whether or not we're picking the right features. So it means maybe we want to add some features to it, maybe we want to transform the features that we have, and depending if we're in the right domain, we're starting with the right data, things might become very simple or they might be very difficult to do, right? And so in the past, very often these were domain experts that would decide maybe for a picture, maybe you want to transform it into a Fourier domain or you want to do this or that, because these might be good features to start with. Now, wouldn't it be nice if this transform itself or the features that we want, that itself could already somehow be learned by a neural net, okay? And that's essentially, not by neural net, by some function, and that's exactly what neural nets do, okay? Neural nets, all they ever do is represent a function, a transform, and you can think about, and this transform will learn from the data itself, and after this transform, after this function, we just put on top the standard linear classifier or regression that we have done already in the past. And so all we do with the neural net is trying to find a suitable transform, a suitable domain, a suitable set of features from our original input data. Okay, so that's all it is. So, what does the structure look like? It looks very simple. So we assume, as always, that we have our data. And so this is the training. And so this data is of the form the xn and the yn. And so in particular, we assume that the xn are real valued in some domain D or in some dimension D. And so what the neural net will be is, I'll draw you a graphical representation. So for each of these D original input features, we'll draw a node. And in this node, we'll feed in our data. So this will be feature number 1 from this data up to feature number D. And so there will be two indices, a subscript, which is the index, the feature number 1 up to D, and there will be a superscript, and the superscript will be there. 0 mean it's the original data, and there will be a sequence of transforms, a sequence of layers, and each of these layers will get then an index that's counting. Okay, so this is the layer 0. And so now what is a neural net? The graphical representation is that we're having now several such layers. And on each layer, let's assume we pick a certain number of such nodes. Let's assume this is K. So in the input layer we have D, and let's assume that each layer later on has K such nodes. So the first layer here, the data will have been transformed to, this is on layer 1, the feature 1, and this goes down to layer 1, and the feature will be some capital K. And then we'll transform this further into, on layer 2, we have feature 1, up to layer 2, we'll have feature K. And of course, you know, there will be infinitely many variations, which we'll talk about later on. There's no reason that this will be D and then all these layers will be K. We could have different numbers. We can have different architectures, but right now we talk about the plain vanilla one. So at some point there will be then, let's say, layer L, or let's say layer L minus 1 and feature 1. This is layer L minus 1 and feature K. This goes to layer L, feature 1, layer L, feature K. And this goes on until we have reached the final layer. And so the final layer, let's assume there are capital L such layers, feature 1 up to L, feature K. And then finally, we'll have our output. And as I said, the output, so this will simply be the output here. And so the output will be something very simple. We'll still talk about it. So the question is now, how do we go now from the various layers? How do we move from one layer to the next layer? So this will be a feed-forward network. We'll take the information here, the data here, and we transform it layer by layer until we finally get to our output. Okay, so this is the structure that will transform the data. And essentially, we're thinking of the first one up to here, just the transformation of the data. And then from here to here, that's then basically our prediction or regression. Okay, so the first part, the first L layer, they just represent a transformation of the data. So how do we do transformation of the data? Well, kind of in a very simple and natural way. What we do is that every point here, every data point here, will be connected in our architecture to all the inputs from the previous layer. And associated to each of these edges here, there will be a weight, right? And so the weight will be, it goes from layer 0 to layer 1. So we write here W0 to layer, we go from layer 0 to layer 1. So we're going to write here the 1 on top. Okay, the 1 will be the same as the 1 here. And then we go from node here, let's say 1 to node 1. So we're going to write here a 1, 1. Okay, so this is simply a weight, and we'll see what we do with this weight. And so the generic form going from layer L to layer L minus 1 will be that I have, let's say here, node I have here node J, and I have a weight associated to it. That is the weight that belongs to the Lth layer. There's an L here, and I go from I to J. Okay, so this will all be parameters, and all these parameters are then things that we can later choose and that we will learn. And so now, what is the function that brings me, let's say, so let's assume I know already all the points here and all the numbers here. How do I compute, let's say, this number here? So how do I compute on the Lth layer the node number J? Okay, so the way we'll do it is that this output here on the Lth layer will be a very simple function. It will be, we'll take the sum. Let me write I. So we take the sum over all the nodes in the previous layer. We'll take their value. So what is the value? This is xl minus 1 because it's the previous layer. And this is node or the value I. We'll multiply it with the weight. So there's the weight at level L from I to J. Okay, so in order to compute what the value here is, I'll take all the values here. For each of the value, I multiply the value with the weight that I've written here. I sum all these things up, right? Then I add what's called a bias term. So there will still be a term here that is sitting here. So there will be still here associated to a bias term, BLJ. It's another constant that I have to learn, another parameter I can learn. And so all I have right now is a linear sum of the inputs on the previous layer with particular weights, the bias term that I have in here. So far everything is linear. And now the only thing that's magic here is that on top of it, outside, I apply now to this sum a nonlinear function. So this function is what's called an activation function. Okay, that it's called activation function simply comes from the fact that neural networks originally came from really trying to understand the brain. And so, that's why it was called activation function, because there were electrical signals coming into one of the synapses, and people were thinking of, once there's this input, once the input from the previous synapses were large enough, this whole synapses got activated, and how it got activated was described by this function. For us, makes no difference where this comes from. It's simply a function. This function is nonlinear, and so there are many possible such functions we can fix, and we'll talk about some later on. Right now, let's think, to be concrete, of this function to be something that essentially we already know. Okay, so this is called the sigmoid, and it's a very simple function, right? It's a function that, of course, we already saw. It's a very simple function. It looks like something like 1. It's a function that monotonically goes from is increasing and goes from 0 to 1, and is symmetric around 0, around the y-axis here, and takes on the value half at 0. Okay, so let's assume that's the activation function. What's important here is that it's some typically always increasing functions. We'll talk about many other shapes. One of the crucial points in here is that this function is nonlinear. Okay, if we didn't have this nonlinear function, and we took this function here to be the identity, right, then what would the overall function be that we have, right? So let's start again. We start from here. For each point here, we take the weighted sum of all the inputs here. This gives us a number. We add the bias term to it, and then we apply this nonlinear transform, right? So now we get all the numbers here. From this to here, we do the same thing. For every node here, we take the weighted sum of all these things here. All the weights are parameters. We sum it up, add the bias term, take the nonlinear function, right? And so in a feed-forward fashion, we start from here to slowly transform this input into some other, into something else, right? So this whole thing here represents a function from Rd to Rk, right? All this is, it just represents a function. And this function is parameterized by all the weight terms and all the bias terms and what kind of activation function we pick, right? So these are the choices we have. Typically, the activation function is fixed. And so what we learn typically is, given the samples, will be, and we'll see how to do it, okay, will be these weights and the biases, right? So that's how we will train the network, and we'll see that the training will be something very simple, stochastic gradient descent, something that we have done many times, and that's how we train the network. So let's assume we didn't have this nonlinear function, and we had simply the sum as it's written here, but not this thing here. Then what would the overall function be? If we didn't have the fees were just, were just trivial, then what would the function be globally, just from one end to the other end? Maybe I heard it already, but okay, I'm just trying to drive home why it's important that this function is nonlinear. Yeah.
Otherwise, we can only have a linear combination of parameters.
Right? It would just be linear in total, right? Because this thing here is a linear combination of that. If we didn't have the nonlinearity here, this one would be a linear combination of of these points, but each of them is already a linear combination of this. So this means this would then otherwise just be a linear combination of the points in here, right? There wouldn't be any point of having several layers because the global function would just be a linear function, and there would be no point of having a complicated layered architecture if all I want to represent is a linear function, right? And also it's clear that if the only transforms we allowed were linear functions, probably wouldn't be a very powerful representation, right? So we'll talk very soon about what these functions can represent. We'll see that they're actually very powerful. They can represent any reasonable functions we want. Okay, so that's already good news. And so they're much more powerful than just a linear transform. Now, how many layers typically in an architecture would you have? Okay, we'll see that in principle, if it's only about representing functions, we need actually very few. Just having a single, so this is typically called the input layer. Here we would have defined the output layer here. And everything in between is what's called a hidden layer typically. And so we will see that even if we limit ourselves to a single hidden layer, so just input, single hidden layer, and then output, as long as I allow the k to be large enough and have a reasonable function, an activation function, I can represent essentially any reasonable, sufficiently smooth function. Okay, so even with a single layer, these networks are already very powerful. But it turns out that in practice now, when people have enough data, in the beginning, some years ago, you would have 1 or 2 layers. These days, people might have hundreds of layers, actually. Okay, so typically networks tends to be better when they are relatively, not very wide, but actually relatively deep. Okay, and so that will cause a lot of other challenges in terms of training and so on. We'll talk a little bit about it. But it might very well be that you have hundreds of such layers stacked up. Okay, so it can get quite complicated. Good. Any questions about the general form of what these networks look like, what we do? Okay, so that's it. That's a neural net. There are 1,000 different variations of it. We'll talk about some. But are there any general questions about what these neural nets do? Just trying to make sure that I don't forget anything. All fine? Yes? How can you choose? How do we choose these parameters? Okay, so we have now all this thing here. From here, if I go from here to here, all this thing represents a function, right? And this function will be parameterized by all these weights and so on, right? So there will be a lot of parameters in here. In such a neural network where I have a fully connected neural network, well, how many parameters do we have here, right? We have in each layer inside here, we have about k squared parameter, right? Plus then the weights here. And then we're having roughly on the order of k squared L parameters. This is not exact, but that's kind of the leading order, right? So there are a lot of these parameters. And so now your question is, how do we pick these KL parameters? Good question. And we'll see how to do it. Okay, so we'll talk about the learning algorithm. The learning algorithm will be similar, what we always do. We'll have some samples. So we'll have certain inputs. And we know what the desired output is, right? And now, given that you have a fixed set of parameters already there, you can check if you're doing well or not. And then we'll simply apply a stochastic gradient in descent, right? So we see how well we're doing. And we're trying to improve this performance, this cost function that we have by tweaking the parameters a little bit and computing the derivatives of all these parameters with respect to the cost function that we have and slowly converging to it. So we'll do what's called straightforward stochastic gradient descent, right? The only thing is we'll do it in a smart way. If you didn't do it in a smart way, it would be a lot of work, right? Because you have there's a very large such gradient vector. And if for each of them you would have to compute the derivative, this would be a lot of work. Okay, so there will just be a smart way called backpropagation that computes this all in one swoop. But other than that, it's straightforward stochastic gradient. You have the gradient, you go a little bit towards in the opposite direction, you have a new one, and you hope that it will converge to something meaningful. That's it. Any other questions? Good. So then what we'll do for the rest of today is, okay, so before we get into the details, how we train, what variations there are, how these things perform, what tricks people have come up with to make them work better, is the question will be, the following. If we hope that we can do something with this, then hopefully by tweaking these k²L parameters that we have in here, we'll hopefully can represent many different functions. And that's what I mean with representation power, right? So hopefully if I gave you a function, let's assume first just in the reals, and then maybe in one-dimensional scalar, but then you can think about in 2 dimensions, 3 dimensions, etc. And I gave you a function already beforehand. Well, hopefully this function can be closely approximated by some particular choice of these k²L parameters, right? Because when we want to learn, we have 2 problems. One is, can we represent the function at all, right? So that means how powerful this is. And the second one is, how, even if we can, how do we find the parameters that represent it, right? So how can we find it? This is what we just talked about. We'll do stochastic gradient descent. But even the best learning algorithm can't do anything if the functions themselves are not powerful enough to approximate a reasonably large class of functions. So if this family could only represent linear functions or something very limited, then it probably wouldn't be worth talking about it, right? And so the question is now, what can we do? And so what we'll do today is, essentially we'll do proofs by pictures, okay? It will be very simple. But there's some very powerful and rigorous mathematical statements out there. So in the notes, I'll give you several. So one is by Baron. And so all I want to do is to write down what the statement is. We're not going to prove the statement. It's not super complicated to prove. Would maybe take 2-3 hours to go through it. And if you're interested in next year, we'll have a learning theory class and we'll go through the proof. But I just want to give you the statement, and then we'll basically prove a simple version of the statements by pictures. Okay, so let me just write down the statement and then we discuss what it means. So we take a function, and let's assume this function goes from, we think of right now of a scalar function that has an input d, a dimension d. And we ask whether or not there is a neural net that has this form which can approximate this function. Now, we'll have to put some conditions on this, that we can do a good approximation. And so there are many versions of this theorem, but typically there's always kind of some smoothness requirement. Okay, we want that this function is reasonably smooth, and there are many ways to describe what that means. One is to look at the Fourier transform, and so we'll require the following, where f, okay, what we want is that where f twiddle, okay, so this is the Fourier transform. And we require that this Fourier transform has the following property, that we can integrate it Okay, so all this says is that this is the Fourier transform of this function. And what we're saying is that this Fourier transform doesn't blow up too much. Okay, so this is, think of in one dimension, it means that towards higher and higher frequency, the Fourier transform dies out sufficiently fast. Okay, it dies out faster than, we multiply it here by x itself. Okay, so it has to die out sufficiently fast that this whole thing becomes integrable and is less than some constant here. Okay, if you know what the Fourier transform is, great. If you're not so sure, all this means is that this function, it's one way to make mathematically precise that this original function here is sufficiently smooth. For example, one condition of this is that the function itself is continuously differentiable. Okay, if this is true, then it means that the function itself that you started with is continuously differentiable. Okay, so we could have asked maybe for that condition itself. Okay, so if that's true, then the statement is the following. Then for all n, we have the following. There exists Fn, and I'll tell you, so Fn will now be exactly a function that looks like one of these neural nets, and I'll tell you a little bit exactly what the form of this function is. I guess we write it down here. So this Fn is allowed to have n components in the sense that it has n, so this k here is now this small n. And okay, so what does this mean? It means the following. We're looking at a neural net that has, as I said, a single hidden component. So there will be the input, and then there will be a single hidden layer. And for each of these hidden layers, for each of the nodes in the hidden layers, this function is exactly what we had written down. Okay? It takes for the j, this is written in vector form here, but if it wasn't written in vector form, it simply would mean that for whatever the jth such input, you take the weighted sum of all the input bits with weights w, you add the bias term, and then you apply this cost function phi here, the activation function phi. And then what you do with this, you're allowed to take n of these nodes in the hidden layer. Okay, so there's n. And you simply sum up these n contributions that you have. Okay, so you have input layer, a hidden layer with n nodes, and then you sum up all the contributions. Is that clear? So it's a very simple structure, much simpler than I wrote out here, right? So it's a case where I have only basically capital L is here 1. Okay, I have only one hidden layer. Is that clear? Okay. So if you have a function that's sufficiently smooth, then if you choose these parameters here properly, right? There exists a choice of these parameters such that this function here will be a reasonable approximation of the original function that I start with. And so now we need to define what it means to be a reasonable approximation. It says the following: as long as I'm just looking at all the points within a sphere of radius r, so I'm looking in a bounded region, okay, as long as I'm just concentrated on the function in a certain bounded region around 0, and I'm looking at the average distance squared. So I'm looking at what is the original function value minus what is for this approximation the value, and I'm looking at the L2 here. So this is just the L2 norm between the two within a ball of radius r. Then I can make this, I want to have this to be small, and so now this is where all the thing comes in. It has small 2cr squared over n. Okay, so that's where all the whole meat of the theorem is. So let's look. So the more nodes we allow, the smaller we can make the error, right? That makes sense. If I have more such nodes that are for the representation, for the approximation, I can make it smaller. The really nice thing is, and that's not trivial, is that I can make it go down as fast as 1 over n, the error. Okay, number one. Number two, you can see that the smoother the function is to start with, right? And remember, the c had something to do with the smoothness of the function. The faster these tails of the Fourier transform go down, the smaller this thing will be here, the smoother the function will be. If this smoothness, the smaller it is, the smaller the error will be, right? You have the c up here on top. Second of all, if I want to approximate a function in a small region, R, then again, the R is here on top, right? Then I need fewer ones. If I make the region larger and larger, I will need more and more of the nodes to do the approximation, okay? So intuitively, I hope this makes sense. Mathematically, as I said, it's not super difficult, but it's a very nice and elegant and non-trivial result, okay? We're not gonna go through that here. If you're interested, next semester there is a learning theory class where we'll do this. Any questions about what this theorem says? Right now we're just trying to understand what it says.
Can you just repeat the part where you said that the error was going down the higher the radius?
So what I'm saying is the following. What does this theorem say? So let's assume we are in 2 dimensions, right? So then the question is, this guarantee is not a guarantee of the approximation of the function over the whole plane, okay? It could be, the approximation could be arbitrarily bad if I go out. What it says is that around the origin I can approximate it. And so I can approximate it, of course, the better, the smaller I pick the region where I want to approximate it. Okay, it's easier to approximate it in a small region than in a very large region, right? And that's exactly what it says here. It just gives a quantitative version here, right? It says that the error that I can guarantee goes up if I want the approximation to be valid in a higher, in a larger domain. Okay, it behaves in the correct way. So it goes down the more nodes I give you. It goes down the smoother the function is, and it goes up the larger region I want this approximation to be true. Okay? Now, yes? Okay, so we want a function, and we'll look at this function in a bounded domain. We'll look at it in, let's say, in a radius, in a region of radius r, okay? Now, in order to have a decent approximation, I need to give some restriction on the function. And there are many ways we could do this. And essentially what we want is it's kind of obvious that functions that are smooth are easier to approximate than functions that could constantly wiggle around, right? If you had a function that could arbitrarily fast wiggle around, then it might be very difficult to approximate it, right? And so there are many ways mathematically how you could capture it. One way is by means of a Fourier transform. And so this is the Fourier transform, and this has to do with the frequency. So just think about it in a one-dimensional setting. You can represent any signal as a superposition of elementary frequencies. And the smoother the function is, the less contents it has in high frequencies. High frequencies are exactly these wiggles, right? And so to capture that this is one way, right? If the spectrum contained many high frequencies, so the high frequency content would go down only very, wouldn't go down fast enough, then this wouldn't become integrable here, right? This would diverge, right? And the faster this goes down, the smaller you can make that. Clear? So it's just one way of describing that this should be a smooth function. There are many other ways how you can do it, and many other theorems that would describe how to do it. Okay, so important here is the following. Our approximation that we're asking for here is, in this case, in L2. And this is only one particular choice, right? It's an approximation in average. We're not asking that the function at any particular point is a good approximation. We're just asking it that in average is a good approximation, right? And so there are many ways in average we could ask. We could ask L2. We could ask it to be in L1, right, where we would have just the absolute value, for example. But we could also ask that, for example, the maximum error, this is called L infinity, and we'll talk about it a little bit later. We could also ask that this is a good approximation in the worst case. Is it clear, the differences of those, right? So if I give you a function, and maybe this is the function I have, and so now maybe this is my approximation that I have, then there's many ways in how the criterion of how we judge whether that's a good approximation. What we have asked is that this difference squared integrated, that should be small, right? We could have asked that this difference, the absolute value of this difference integrated is small, or we could have asked, for example, that the maximum in the region is small. Okay, so there are many different versions that you can do, and so they will give you slightly different mathematical statements. We'll talk later on about still one version where we have an L infinity approximation, okay? But right now, you know, for this, let's just think about that particular case. Yes?
We do not have any dependence on the dimension of the input.
Yeah.
That's strange.
Yeah, well,
I would guess that there it should not be R squared, but F to the D.
no,
Maybe Y should be like related to the volume.
no, you know, you have, of course, you have this in here too, right? You have, of course, some dependence in the dimension in here, right, for the C, right? I'll check it out again, but I'm pretty sure that that's actually correct, okay? But it's a good point. Good. Any other questions? So for the whole rest, all we'll do is we'll draw some pictures, and we'll basically try to explain to you a qualitative version of this, why this is true, but it will not be nearly as powerful, okay? I'll just show you that whatever you want, as in terms of this, you can find, if let n go to infinity, you can find an approximation, okay? And we'll just do that also by pictures. But nothing of this will be quantitative, okay? The way I will explain it it will be obvious, but in general, if you actually went that route, you would need, the dependence on n would be much worse, okay? You would need many, many more points. Okay, but it is a very nice and very intuitive and graphically pleasing way to understand this. Yes, please.
Does that result with any specific activation function in mind?
Sorry, I didn't mention this. So these are for all what's called, you know, in the, so for example, it would apply to the sigmoid, that thing, but this is much more general. So they just have to be sigmoid-like. Okay, so sigmoid-like means it has to have limits in the two and some nice transition. Okay, but this applies to a very general class of activation function. Okay, and in particular for the sigmoid it would apply. Good. I suggest we take a break. Okay, when we come back, we'll do the